Hi, I'm Jason Posner. I am advised by Professor Tseng at Boston College, and I will be presenting our paper, Federated Vehicular Networks, Design, Applications, Routing, and Evaluation. Before presenting our project, I'd like to discuss some of the observations of vehicular networks. Many vehicles of today are equipped with a rich set of computing and communication resources in their onboard units. And this has led to the general concept of vehicular networks and also the recently emerging concept of vehicular clouds. However, standard vehicular networks are often unstable due to vehicles constantly moving in and out of the network and therefore a rapidly changing topology. We therefore propose the idea of a federated vehicular cloud. That is, vehicles stay in a fixed location most of the time so that the connection is stable. Now, of course, such a vehicular cloud model cannot be applied to all situations, but we believe there are a multitude of applications that this could support. Some of these are virtual infrastructure for entertainment at sports venues, as well as reliable distributed machine learning within vehicular networks. In our paper, we aim to present a high-level design of an FVC, and given our design, propose algorithms to minimize the cost of routing content between two vehicles in the network. Before this, we should also discuss the prior work which has motivated our research. Firstly, there has been extensive research in cloud computing models for vehicular networks. However, none of these have proposed a stationary vehicular network for cloud computing. Secondly, there has been work on vehicular communication protocols such as millimeter wave and DSRC, and these will be the standard for almost all autonomous vehicles in the near future. Using these, we'd like to utilize the inherent benefits of FVC for a more centralized computing model. And given our constraints, including those that we make on our communication protocols, we want to solve the inherent routing problem in such a model. For communication between vehicles in our network, we assume that each vehicle is equipped with dedicated short-range communication and 5G millimeter wave. DSRC supports about 10 kilobytes per second in practice and has a range of about 200 meters. Millimeter wave, on the other hand, can support a bandwidth on the order of a few gigabits per second and has very long range, which is strictly directional. We let standard vehicles in our network be equipped with one rotatable millimeter wave antenna and have DSRC communication. We also assume there to be more powerful vehicles in our network with multiple millimeter wave antennas, which we will call super peers. Lastly, we assume that each vehicle is aware of the locations of nearby vehicles. While in certain cases getting perfect geographic coordinates is not possible, such an assumption is feasible because we can always use heuristic approaches such as georouting to obtain a close estimation. An FVC consists of three main components: the venue infrastructure, worker nodes, and proxy nodes. For communication within the network, we use DSRC communication for control messages between close vehicles, and millimeter wave is used for data transmission in the network. The venue infrastructure represents the infrastructure within stadium, malls, and other venues which allow clients to send signals in and out of the venue. Worker nodes in the context of an FVC are the vehicles which can cache and deliver content. Lastly, proxy nodes, which via DSRC communication are aware of each item that is cached within the network and its location. They also communicate with the venue infrastructure to notify it of any changes of cache allocation within the network. The flow of serving a client request would then be as follows. Firstly, the client would have a content request for some piece of content. This request would then get sent to the nearest available venue infrastructure. If this content is stored within the FVC, the infrastructure would forward the request to the nearest proxy node. Otherwise, it would be handled using previously existing protocols such as contacting internet cloud or content delivery networks. The proxy node would then forward the request towards the vehicle which stores the content, and this vehicle, now acting as the source, would find a path back to the proxy using some routing protocol. Finally, the content is sent back towards the proxy, and the proxy would send this content back towards the venue infrastructure, which is then forwarded to the client. Vehicles can also leave or join the network through a DSRC-based communication, where proxy nodes are informed of which vehicles are leaving or going. We represent our network as a directed dynamic graph. Each edge in the graph would have an associated weight, which is a random variable in the closed interval A to B, where A and B are greater than 0 and A is less than B. Each node also has a positive flow capacity and a non-negative flow at time t. For standard vehicles, this flow is specific to the node and not the edge, since each standard vehicle only has one antenna. We have that each antenna can rotate if and only if the flow is zero, to represent the fact that a vehicle cannot transmit data to another vehicle until it's finished transmitting to the current vehicle. We also give each node a fixed rotation speed for their antenna. As stated before, we want to minimize the latency when routing in our network between two nodes. And for this, we propose 3 different routing algorithms. Our optimal routing algorithm reconstructs our dynamic graph into a static graph, where the set of edges, E prime, includes every possible routing option for each node. There are 2 cases here. If our node is able to rotate, then we assign weights to all of its edges with the value of the expected cost. In this case, the expected cost is the expected latency plus the time it takes to rotate. If our node is unable to rotate, we assign all weights to infinity, except the node it is pointing to, in which case the expected cost equals the expected latency. Since there are at most 8 V edges, this can be done in linear time. Then to find an optimal path, you can use any shortest path algorithm. Our next algorithm takes the greedy approach and tries to make the locally optimal choice. There are 2 conditions for choosing a neighbor to route to. 1, we want to choose a neighbor that's actually closer to our destination. And secondly, we want to choose a node that has the freedom to rotate. In other words, it has no flow on its antenna. Of the nodes that meet these conditions, we want to choose the one with the lowest expected cost. For divide and conquer, we're motivated by the fact that DSRC protocol can usually not exceed 200 meters. Therefore, our approach for the optimal algorithm is infeasible, since we won't have enough information from the source to reconstruct our graph entirely. Therefore, instead of routing to our destination, we can route to some intermediate node instead. We then run the optimal algorithm to this node, and finally this node becomes the source and repeats the process until we reach our destination. With these algorithms, we simulated an FBC using Python and NetworkX, which is a network simulation library in Python. We arrange the vehicles in an M by N grid, and the weights are random variables following a uniform distribution. Content requests arrived according to a Poisson distribution with rate parameter of 10 requests per second, and simulations are run for a total of 100 seconds. The plot here shows how the average latency is affected as the number of nodes in the network are increased. As we can see in the plot, the optimal routing algorithm performed the best, followed by the divide and conquer algorithm, and then finally followed by the lowest cost algorithm. In summary, this paper proposed a high-level design of an FBC, formulated the routing problem in an FBC, proposed 3 different potential algorithms, and finally implemented a simulation framework to test our algorithms. While we've laid a general framework for FBC in this paper, there still remain many future research directions and open problems. One large one is addressing fault tolerance in the network. Some others include churn in depth, generalizing communication protocols beyond DSRC and millimeter wave, and also caching and scheduling algorithms. We hope our work here will inspire research in these and other related areas. Thank you.